I made a generative adversarial neural network that could generate seemingly authentic handwritten letters, which turned out to be even better than my own handwriting. Wow, that's so cool! How did you manage to do that? I'm glad you asked. GANs are, in my opinion, the most exciting class of neural networks that push the boundary of what neural networks can do. They use sets of existing data to learn how to create new data, fake data. GANs are solving a variety of problems, like morphing audio, improving image quality, or even generating new data for another model to train on. GANs stand for Generative Adversarial Neural Network, and they are used for generative modeling. That's where the generative portion comes from. They are made up of two fighting neural networks. That's where the adversarial portion comes from. Okay, so what does a GAN structure look like? The two neural networks inside of a GAN have different roles. The first one, the generator, tries to create fake images to trick the discriminator into thinking it's real. On the other hand, the discriminator, which is the second neural network, tries to not be tricked by the fake images created by the generator. A discriminator is a classifier, meaning it classifies its inputs into two groups, fake or real. The fake inputs are used as negative examples, and the real inputs are used as positive examples. Then the inputs are fed into a series of layers. The accuracy is measured by how well the model differentiates between two kinds of inputs. With training, the model gets better at classifying its inputs, and hopefully, in the discriminator's point of view, doesn't get fooled by the generator. On the other hand, the generator wants to trick the discriminator by generating fake values. Then, for some feedback, it goes to the discriminator to see what it thinks, and depending on if it got fooled or not, it gets penalized. Training these networks are done in two steps. Firstly, you run through the model and then you calculate the loss, or the accuracy, and then you backpropagate. This is the process that adjusts the parameters for better accuracy. Here's a simple overview of how my code works. First, I'm importing all the modules that I need to get started. Then I'm defining some important helper functions. The first one is to show the data. The second one is to denormalize, which is important to show images. Here I'm creating my dataset by reading a CSV with all the images that I have. I realized that there were 50 times as many O's than F's or I's, and probably 20 times as many S's than X, Y's, or Z's. So this code is how I fix that. Here I am converting the dataset into a NumPy array, and I'm reshaping it to 28 by 28 so I can show the images. Here I'm normalizing the dataset, which converts values ranging from 0 to 255, for each pixel by the way, to values ranging from -1 to 1. Because the generator outputs values ranging from -1 to 1, and the discriminator needs to compare apples to apples. Here is where I convert the dataset into a torch tensor. Here I define a data loader, which I'm going to use for training. Here is where I'm defining my discriminator network. If you remember correctly, it takes an image as an input and tries to classify it as real or generator. While we can use a CNN for the discriminator, I just stuck with a simple feed-forward network with 3 linear layers. I'm using a leaky ReLU activation because it allows the pass of small gradient signals for negative values, and it makes the gradients from the discriminator flow stronger into the generator. Here I'm defining the generator network. Its input is typically a vector or a matrix, which is used as a seed for generating an image. It has completely random values. To keep it simple, I just used a feed-forward neural network with 3 layers, and an output with a vector of size 784. Note that I used a hyperbolic tangent function. This outputs values ranging from -1 to 1. I used a loss function of binary cross entropy because I was dealing with a binary classifier. I used an atom optimizer for both neural networks because they converge faster. So here's how I trained the discriminator. First, I run through the model using real images as its inputs, and then I use real labels of ones to calculate the loss. And then I calculate the fake loss by running fake images through the model and using fake labels of zeros to calculate the loss. To calculate the total loss, I add them together, and then I perform gradient descent to tune all the parameters. This is how I train the generator. First, I run through the generator, and then I set the labels to ones because the generator wants to try and trick the discriminator. Then I see what the discriminator thinks, and then I calculate the loss. So here is how I trained the GAN. I use 450 epochs, and I call both training functions. And then I document everything so I can see how good it was by graphing the losses. That's all, folks. Thank you so much for watching. If you want, subscribe to me and my newsletter in the description below, and I'll see you in my next video.